Kinematics in one dimension. Free response problems. For problem number 1, a car travels in a straight line along a road. Its position x as a function of time t is represented by the equation x of t is equal to at squared minus bt cubed, where a is 1.4 meters per second squared and b is 0.06 meters per second cubed. A. Calculate the average velocity of the car for the interval t is equal to 0 to t equal 3 seconds. For B, we're going to do the average velocity from t equals 0 to t equals 5. And for C, we're going to do it from t equals 3 to t equals 5 seconds. Hello everyone. So today we're going to do the free response problems from the NJCTL page for AP Physics C, Kinematics in one dimension unit. So we're just going to do the first 5 problems and then we're going to do the other ones later. So for number 1 we already have the function, the position function x of t is going to be at squared minus bt cubed, right? And we said that a is 1.4 meters per second squared and b is 0.06 meters per second cubed. Now we can already substitute those values in there, so it makes our lives easier. So let's just change that into 1.4 t squared minus 0.06 t cubed. Okay, that's the position function that's given to us. Now for the A, B, and C, we're just going to calculate average velocities given the time intervals. So we're going to go ahead and do time intervals from t equals 0 to t equals 3. So, and B is from t equals 0 to t equals 5. And C is from t equals 3 to t equals 5 seconds. Now there are 2 equations for average velocity that you have to know for the AP Physics C exam, and those are the following. So there's the average velocity, when you have a change in position, in other words displacement, divided by the change in time. So this equation over here is just the general equation for velocity. This is the definition of velocity or average velocity, and it can be used for any type of function regardless of whether acceleration is constant or not. So who cares if acceleration is not constant or is constant in this problem? We can use this problem and it will apply for those type of problems. But there's also another definition for average velocity, which is a special case of a velocity. When you have the initial velocity plus the final velocity and you divide that by 2. So it's an average, right? But the problem with this equation is that it has a constraint and only works when the acceleration is constant. So acceleration has to be constant. It must be constant. And how do we find that out? Well, the only way to find it out is if we find the acceleration function. So let's go ahead and take the 2 derivatives, the second derivative of position. So second derivative of x of t in terms of time, right? d squared x of t over dt squared, which is second derivative. That's going to give us acceleration, a of t. So first, let's take the derivative of position over here. So we're going to get d over dt of x of t, it's going to give us 1.4 times 2 is 2.8, right? T minus 0.08, minus 0.18, right? 6 times 3 is 18, t squared, and that's going to give us the velocity function. So let's take another derivative, right? So d over dt of the velocity function that we just found out is going to be 2.8 minus 0.36 t. Now this is the acceleration function. This is a of t. But this the problem with this function is it depends on a linear relationship with time. It's not constant. So that means acceleration is not constant and we cannot use this formula. So we're going to have to use the original definition of velocity, which is, okay, changing changing position over changing time. So displacement over time. So let's go ahead and do that. So we're going to get the following. So we just have to plug in the values for, okay, displacement for the given intervals, right? For the given intervals. So we're going to do the position function, right? 1.4, and then we're going to substitute the time for the. So we're going to do something like this. We're going to do x final minus x0 divided by t final minus t0, and we know that t final is t when t equals 3 seconds, and t0 is t equals 0, right? So we're going to do that the average velocity for part A is going to be, okay, the position function evaluated at the final time, so 1.4 times 3 squared minus 0.06, okay, times 3 to the power of 3, and all of that divided by the change in time, so 3 minus 0 is 3, and we can go ahead and plug that into the calculator. So I got my own virtual calculator here, so I just gotta go with my phone. There is an app on the Play Store that's called Wabitimu, and you can use that, okay, as a simulation for TI-84, and it's pretty useful, honestly. So I think you could use that when you go to class, but of course you're gonna get a calculator when you go and take the AP exam. So let's go ahead and plug those values into the calculator and see what we get. So we got 3.66 meters per second. So 3.66 meters per second. So that's going to be, okay, the average velocity from 0 to 3 seconds. So on that time interval. Now let's go ahead and do part B. So from 0 to 5 seconds. Okay, so we're going to apply the same formula for average velocity. And we're going to do the same thing, x final minus x0 divided by t final minus x0. The position function evaluated at the final time, which is 5, so 1.4 times 5 squared minus 0.06 times 5 cubed divided by the change in time. 5 minus 0 is 5. And we can go ahead and plug that into the calculator. Remember that you have to, okay, have a calculator for your AP exam. You might not want to do, you might not want to forget your calculator. So let's go ahead and plug those values. So we got 5.5 meters per second. 5.5 meters per second is the average velocity in the time interval from 0 to 5 seconds for this position function. So let's go ahead and do part C. So the time interval is from 3 to 5 seconds. So we're going to do the same formula. So average velocity is equal to x final minus x0, right, divided by t final minus t0. All this over here has to be t0. Yeah, made that mistake. Okay, so we're going to do the position function, okay, evaluated at 5 first, again, right? Oh, wait. Yes, so I forgot to tell you that I forgot to evaluate the position function at t equals 0 because we already know that it's 0, right? So it's kind of obvious. But for this one, it's a little different, so you will see why. So minus 0.06 times 5 cubed divided by the change in time. But that's going to be everything. So because we have to subtract the position function evaluated at t0, right? So t0 in this case is 3 seconds. So times 3 squared minus 0.06 times 3 cubed. And everything, so everything that results from this operation over here is going to be divided by the change in time. 5 minus 3 is 2. And we can go ahead and plug that into our calculator. So let's go ahead and see what we get. So we get 8.26 meters per second. Okay, 8.26 meters per second. That's going to be the average velocity in the time interval from 3 to 5 seconds. Okay. For number 2, an object moves in a straight path. Its position x as a function of time t is presented by the equation x of t is equal to at minus bt squared plus c, where a is 1.4 meters per second, b is 0.06 meters per second squared, and c is 50 meters. For parts A, B, and C, we're going to calculate the average velocity of the object from the given time intervals, from 0 to 5 seconds, from 0 to 10 seconds, and from 10 to 15 seconds. Okay, so for question 2, remember that we're given the position function already over here, and we're given the values for A, B, and C, so we can go ahead and substitute that in so that it makes our lives easier, right? So x of t will be equal to 1.4 t, that 4 looks like a 9, I'm sorry, 1.4 t minus 0.06 t squared, and then c is going to be 50 meters, so plus 50. Okay, so that's going to be the position function over there. Now we're just going to do the same thing we did in the last problem. We're going to calculate the average velocity and, okay, for the given time intervals. Okay, so from 0 to 5 seconds, from 0 to 10, and from 10 to 15. Okay, so for part A, we got from t equals 0, so t0 is 0, and t final is 5. Okay, 5 seconds. Now let's go ahead and do that. So first, we could see if the velocity, if the acceleration is constant. So let's go ahead and see and check if the acceleration for this position function is constant. So we just have to take the second derivative, okay, of x of t in terms of t time. So that's going to be the acceleration, right, a of t. So let's go ahead and take the first derivative. So first derivative of position to get velocity, right, is going to give us, okay, 1.4 minus 0.12, right? And then the derivative of 0.12t, the derivative of 50 is just 0. Then we take another, okay, that's going to be the velocity function. So we take another derivative, so we're going to take the derivative of the velocity function, so dv over dt, and that's going to give us negative 0.12. Okay, negative 0.12 is a constant, so that means that acceleration, okay, the acceleration function is defined by a constant, which means it's constant, right? So that means we can use the other equation, the other formula for average velocity, which is just, okay, v0 plus v final, all of that divided by 2. So to do that, we just gotta write out the velocity function, v of t, which was 1.4 minus 0.12, okay, t, and we have to evaluate the function at the given time intervals, right? Now this makes our lives a lot easier because the velocity function is a lot more simplified than the position function, provided that it's first derivative, right? So let's go ahead and find out the average velocity. So we're just going to calculate the initial velocity at t equals 0, which is going to give us 1.4 plus the final velocity is 1.4 minus 0.12 times 5, okay, all of that divided by 2. So let's do that, let's calculate it, see what we get. So we're going to get 1.1, okay, the average velocity from the time interval from 0 to 5 seconds is going to be 1.1 meters per second. Okay, so let's move on to part B. Oh, I shouldn't have erased the velocity function. Let's write it out here again. Okay, so for part B, we have the time interval from 0 to 10 seconds. So t0 is 0, t final is 10. Okay, 10 seconds. So we're going to evaluate the average velocity in the time interval from 0 to 10 seconds. So we're going to use the definition that says that v0 plus v final divided by 2 is the average velocity. So we just have to add, okay, v0, so that's going to be 1.4, and then we're going to add the v final, which is going to be 1.4 minus 0.12 times 10, all of that divided by 2. This is going to give us 2.8, right? 2.8 minus 1.2 divided by 2. That's going to be 1.6 divided by 2, which is going to be 0.8. So the average velocity is 0.8 meters per second. Okay, so for part B, now let's go ahead and do part C. Part C has a time interval from 10 to 15 seconds. So t equals 0 is 10, and t final is 15. Okay, so we're going to do the same thing. So that's going to be 1.4 minus 0.12 times 10. We're going to add v final. So that's going to be 1.4 minus 0.12 times 15. All of that divided by 2. We can go ahead and plug that in the calculator. Okay.
So let's see what we get.
So the average velocity for part C is negative 0.1 meters per second. Okay, that's the answer. If we use the position function instead of the velocity, it will take us a lot longer to calculate it because we have a squared in here and we have a constant 50. So it's always good to look at whether acceleration is constant or not. That could save you a lot of time that you could use for another question. For question 3, a car starts from a stop sign and moves along a straight road, so its position as a function of time is presented by the following formula. X of t is equal to alpha t squared minus beta t cubed, where alpha is 1.8 meters per second squared and beta is 0.08 meters per second cubed. For part A, we're going to calculate the average velocity of the car from t equals 0 to 5 seconds. For B, we're going to calculate the instantaneous velocity of the car at t equals 0, t equals 5, and t equals 10 seconds. For C, we're going to calculate the time it takes for the car to be at rest again. And D, how far from the starting point will the car be at rest? So for this question, question 3, we're given the position function, right? And we can already plug that in because we know the values of alpha and beta. So let's go ahead and put 1.8 for alpha and 1.8 t squared, and for beta is 0.08 t cubed. Okay, so that's the new position function. This is the position function that's given to us. Now for part A, we're just going to look at the time interval, okay, from 0 to 5 seconds. So t equals 0, t0 is 0, and t final is 5. Okay, so in this case, acceleration is not constant because clearly, right, when you take two derivatives, you're not going to get a constant from the highest power, right? So forget about that. We're going to use the original definition of average velocity, which is displacement over time, okay, over change in time. So we're going to have to use some calculators. So that's going to be x final minus x0 divided by t final minus t0. Okay, so we can go ahead and do that, plug that in there. So let's do the average velocity is going to be equal to, let me actually do it more to the left so it's more space. So average velocity is equal to, okay, 1.8 times 5 squared, right? Minus 0.08 times 5 cubed. And then we're going to evaluate it. We're going to subtract the position function at t equals 0. That's just 0, right? all of that divided by the change in time, which is 5. So let's go ahead and plug that into the calculator to see what we get. So we got 7 meters per second. That's going to be the average velocity in the time interval from 0 to 5 seconds. For part B, we're going to get, okay, and the time interval from t equals 0, so t0 is 0, and t final is 10 seconds, okay? So we can do the same process again. So the average is going to be 1.8 times 10 squared minus 0.08 times 10 cubed. All of that divided by the change in time, which is 10. Now this we can maybe do it without a calculator. So 10 squared is 100, right? So that's going to be 100 times 1.8. That's 180, right? So that's going to be 180 minus 10 cubed is 1,000, right? 1,000 times 0.08 is 80, right? So that's going to be 80. And all of that divided by 10. That's 100 divided by 10, that's 10. So that's 10 meters per second. That's going to be the average velocity on the time interval from 0 to 10 seconds. Now for part C, okay, for part C we're going to have time intervals. T0 is equal to 10 and T final is equal to 15 seconds. Okay, so now we have to subtract something because you see when T equals 0, well, it's so easy. But right here we have T0 is 10. So average velocity is going to be 1.8 times 15 squared minus 0.08 times 15 cubed, and we're going to subtract 1.8 times 10 squared, and then we're going to add 0.08 times 10 cubed. All of that is going to be divided by the change in time, which is 5 seconds. So let's plug this less into our calculator. Okay. Oh, we know that this over here is 80, right? We found out that this is, 100. This value over here on top is 100. So maybe we could make that calculation faster. So we have to subtract 100 over here, okay? So surprisingly we get 7 meters per second again, okay? Just like in part A, okay? Well, that's an unusual result, very interesting. Okay, so 7 meters per second is going to be the average velocity in time interval from 10 to 15 seconds. Okay, we're going to move on to the next question now. For 4, an object moves along a straight line. The position as a function of time is given by the following formula. X of t is equal to 5 plus 2t minus 0.6 t squared. Just remember to remove the units from the formula so that you can work it out easily. A. Find the object's initial position, initial velocity, and initial acceleration. B. At what time will the object come to rest? C. How long after the starting point does it take the object to pass the origin? D. At what time is the object located at position of plus 4 meters from the origin? E. Sketch the following graphs: x of t, v of t, and a of t. Okay, so for question 4, we're given the position function, right? And it's given with the units in it. So what you want to do is get rid of those units and rewrite the position function without the units, right? Because that's going to make your life a lot easier on the exam. So go ahead and do that, and we're going to do part A, which is finding the initial function, the initial values for position, velocity, and acceleration. So what we could do here, is evaluate x of 0. So x0 is going to be 5 plus 0, right? So that's going to be 5 meters. We found out that's going to be x of 0 or x0, right? Now v of 0 is going to be the first derivative evaluated at 0, right? So that's going to be So let's write out the velocity function over here. V of t is going to be 2 minus 1.2 t. Okay, that's going to be the velocity function. And when we evaluate it at 0, that's going to give us 2 meters per second. Okay, don't forget about the units. You have to write out the KMS units. Don't forget about that. Meters per second, okay, with respect to each function. Now let's find out what the acceleration function is. That's going to give us negative 1.2. It's a constant. Okay, so that means a of 0 is, well, same thing, is negative 1.2 meters per second squared. Because it's a constant, okay? We found part A. Now let's go ahead and do part B. So for part B, okay, so what time will the object come to rest? When it says rest, whenever it says rest, it means when the velocity is equal to 0. So we have to find out when, okay, the velocity function is equal to 0. So we have to set the velocity function equal to 0. So 2 minus 1.2 t is equal to 0. We got negative 1.2 t is equal to negative 2. T is equal to negative 2 over negative 1.2. Let's see what that is. If we plug it into the calculator. Okay, so that gives us 1.67 meters per second. That's going to be, I'm sorry, 1.67 seconds. Yes, because we're looking for time, right? So t is equal to 1.67 seconds. That's going to be the time when this object comes to rest. Okay, so let's go ahead and do part C. Okay, how long after starting does it take the object to pass the origin? Okay, so we're going to have to look at the position function. Okay, the position function. And then we're going to have to set it equal to 0. So x of t is going to be equal to 0. So we're going to have 5 plus 2t minus 0.6 t squared is equal to 0. And we're going to find t. If you are to have a calculator on the exam, because you're allowed to, you can use the graphing tool of the calculator to find the zeros of this quadratic function to make your life easy. So let's go ahead and do that. Let's see what we get. So we found out that the object crosses the origin at t equals 5 seconds, okay? At t equals 5 seconds using our graphing tool in the calculator right here, okay? So take a look at that. So at t equals 5 seconds, okay, the position is equal to 0. So the object crosses the origin at that exact time. Let's go ahead and do the next part. So we're going to do D and E. Okay, so for part D, what time is the object located at a position of plus 4 meters from the origin? So we just have to set the position function 5 plus 2t minus 0.6 t squared equals to 4. Okay, so positive 4, right? Don't forget that. And then we get a quadratic function, right? So we get 1 plus 2t, we bring that to the other side, minus 0.06 t squared equals to 0. We can find the zeros of this quadratic. So you can go ahead and use your graphing calculator to find the value of t. So we're going to find the time, okay, when the position is plus 4 meters. So we found out that t is equal to 3.77, okay, seconds. So after 3.77 seconds, the position is 4 meters, okay, positive 4 meters, so from the origin. Okay, let's go to part E. So we're going to sketch the graphs of x of t, v of t, and a of t. So they're going to sketch the graphs of position, velocity, and acceleration. So let's go ahead and graph position over here, x of t. Okay, so we got the x-axis, and then we're going to have t for time. Now, we found out, okay, that at t equals 5 seconds, okay, at t equals 5, right over here, and this is going to be 0, right? And that the initial, okay, the initial position is 5 meters. So this is 5 meters over here. And it's going to be a quadratic going like that, okay? You just have to sketch it. You don't really have to put the numbers, okay? You don't have to label it if you're not asked to. But if you're asked to, if you're specified to label the graph, you must do so. But in this case, you know, we're just doing it because we found the values already. So it's always useful to, okay, label it, even if, okay, if you have time, okay, you should do it. So let's go ahead and do the velocity function, v of t. Okay, so we know that's going to be the derivative, right? That's going to be the derivative of this. So it's going to be like that. It's going to be 2 minus 1.2t. Okay, so this is v of t. When it's equal to 0, so when t is equal to 0, v of t is 2, right? So it's somewhere over there. But let's actually bring it up a little bit. Let's bring the scale up. So that's going to be 2. And it's a negative relationship, so it's going to be like that, right? And what happens when v of t is equal to 0? Well, we found out that's going to be 1.66, right? So this is supposed to be 1.67, right? Seconds. Okay, so that's x of t, v of t. Now let's do the easiest one, really, acceleration. The easiest one, because you will see why. So acceleration is constant, right? It's negative 1.2 meters per second squared. So actually, all we have to do is just put negative 1.2 and make a straight line like that, because it's constant, okay, at all times. So those are the graphs, okay, for this question. Now we're going to move on to the last question for today, question 5. For question 5, a bee flies around a closed classroom. A physics student is able to record the position of the bee as a function of time and present it to his classmates. R of t is equal to negative 9 t I hat plus 7 t j hat plus 10 t minus 4 t squared k hat. A. Present the vector of velocity and acceleration of the bee in terms of unit vectors. B. Find the displacement, velocity, and acceleration of the bee at time t equals 10 seconds. C. Is there a time when the velocity of the bee is 0? And D. Is the acceleration of the bee constant? So we have the position of the bee, okay, as a vector. R vector of t. It's going to be equal to negative 9t I hat, okay? Let's just eliminate the units already, right? We don't need the units, okay? Plus 7 t j hat, okay? And then we're going to have plus 10t minus 4t squared k hat. Okay, so that is the position vector over here. This is going to be the position vector. And okay, so for part A, we're going to present the vector of velocity and acceleration of the bee in terms of unit vectors, okay? So we're just going to take two derivatives, right? So for velocity, so for v, okay, v of t is going to be, we'll just take the derivative of that, right? So that's going to be negative 9 I hat, right? Plus 7 j hat, okay? And then we take the derivative of this in the inside, so we're going to have plus 10 minus 8t k hat, okay? Now let's find the acceleration vector function. So we're going to have negative Okay, no, that's going to be 0, right? This is a constant, this is a constant, that's going to be 0. We're going to be left with, okay, negative 8 k hat. There you go. So those two are the velocity and acceleration vector functions. And we're going to go ahead and do part B. We're going to find displacement, velocity, and acceleration of the B. Okay. At time t equals 10 seconds. Alright. So let's see what we could do here. So we're just going to substitute, okay, the value of t by 10. Okay, so for 10 seconds. So our vector of 10 is going to be negative 9 times 10, right? I hat plus 7 times 10 j hat plus 10 times 10 minus 4 times 10 squared k. Okay? So that's going to be, okay, r of 10 is going to be negative 90 I hat plus 70 j hat, okay, and then this is going to be 100 minus 400, that's going to be negative 300 k hat. Okay, so this is going to be the position vector, right? But we're asked for the displacement, right? So let's go ahead and find the magnitude of this vector over here, okay, to find the displacement, the net displacement. So let's go ahead and find the magnitude of the vector when it's evaluated at 10. So let's go ahead and do Pythagoras, right? So we're going to do square root of 90 squared plus 70 squared plus 300 squared. Okay, let's plug that into our calculator and see what we get. So we got 320.9 meters. But we could round it to 3 significant units, so we could do 321 meters. That's going to be the position from the origin, okay, of the B. So this is going to be the displacement. I'm sorry, it's not going to be the position, but the displacement. Okay, so that's going to be displacement. So let's do now the velocity. We're going to find the velocity, so we have to look at the velocity vector function. So we have to evaluate it at t equals 10. So we're going to do b of 10 is equal to, okay, negative 9 I hat plus 7 j hat plus 10 minus 8 times 10 k hat. Okay, so 8 times 10 is 80. 80 minus, so 10 minus 80 is going to be negative 70. So that's going to be minus 70 k hat. Okay, so this is the velocity vector function evaluated at 10, and we're going to find the magnitude of that vector. Okay, to find the magnitude of the velocity. So we do Pythagoras again in 3 dimensions. So 9 squared plus 7 squared plus 70 squared. I just disregard the negatives because we know that when we square a negative, we just get a positive, right? So let's go ahead and do that. Plug that into our calculator. So we got 70, okay, 0.9 meters per second. So that's going to be the velocity, okay, at t equals 10 seconds. Now let's do the acceleration at t equals 10. Well, that's just going to be negative 8 k hat, right? And when we find the magnitude of the acceleration, okay, because it's constant, right, we're going to have, okay, the square root of 8 squared and that's just going to be 8 meters per second squared because it's a constant, right? So at any time it's going to be 8 meters per second squared. Okay, so let's move on to part C. For part C, we're going to find whether or not there is a time when the velocity, okay, of the b is 0. So of course we have to set the velocity vector function equal to 0. So let's go ahead. Oh, I erased that. So let's just do it again. So it's going to be negative 9 I hat, okay, plus 7 j hat plus 10 minus 8 t, okay, k hat. That's going to be velocity, okay? Now we have to set it equal to 0. We have to set that equal to 0. And we have to find if there's a time when it's 0. Okay, so we have to use Pythagoras in 3 dimensions here. So let's use Pythagoras in 3 dimensions. So we're going to find the magnitude of the velocity, okay, which is going to be the square root of 9 squared plus 7 squared plus 10 minus 8t squared, all of that squared. Okay, and that should be equal to 0. Now let's see what we get now. So well, over here we can get rid of the square because we have an equation that's equal to 0, right? So we square both sides. You know 0 squared is 0, right? And then we cancel out the radical and squared, so we get 81. Okay, plus 49 plus 100 times 2 times AB, right? So we're going to have minus 8 times 10 is 80 times 2 is 160, right? So 160t plus 64 t squared. All of that equal to 0. So over here we could simplify this a little bit. 100 plus 81 is 181, right? So we're going to get 130, okay, 130. So 130 minus 160t plus 64t squared equal to 0. And of course, we can use the graphing calculator to find t. So let's go ahead and do that. So we found out that there is no real solution, okay, for this quadratic equation, and we can show that by finding the determinant, right? So we're going to find b squared minus 4ac, which is just going to be 160 squared minus 4 times 130 times 64. Okay, this number over here is going to be a lot larger than this, which means that it's going to be a negative number, which means that it's going to be a complex solution. So there is no time, okay, when the velocity is equal to 0. It's always positive. Okay, the b is always moving. It's never going to stop unless it gets to bite you, but that's unlikely. So let's see. So there's no time. There is no time. Okay, when the b is at rest. Okay, so that's the answer. Now let's move on to part D. Last question. Is the acceleration of the b constant? Well, we found out that it was constant, right? Because when we take the derivative of this again, we were going to get, okay, the acceleration, right? And we get that this is 0, this is 0, and this is going to give us negative 8 k hat. When we find the magnitude of the acceleration vector, okay, we get that it's going to be the square root of 8 squared, which is just 8 meters per second squared. So the acceleration is always constant, okay? It's always 8 meters per second squared, so yes, acceleration is always 8 meters per second squared. So it is constant. Okay, so that's it for today. I'm gonna keep posting videos on the free response problems on the NJCTL page for kinematics in one dimension and other units. Thanks for watching. Please subscribe, give it a like, and share. Okay.